In the last presentation, we completed the ring counter, we saw the circuit, we formed the table, and we also saw the waveforms. Now we will study another type of counter that we call as the Johnson's counter or twisted tail ring counter. If I compare these two counters, I will say that the Johnson's counter is much better than the ring counter that we studied in the last presentation. I am having two reasons for it. The first one is the number of state. If you remember, in the last presentation I told you the number of state is equal to the number of flip-flop used, and we used 4 flip-flops there, so the number of state was 4. But in Johnson's counter, the number of states is equal to twice the number of flip-flops. So if I use 4 flip-flops, I will have 8 states. So the number of state is double here as compared to the previous case. So this is a much better counter. There is one more advantage that I will explain you when we will fill this table. Now let's see what are the changes that you have to make in the circuit to get the Johnson's counter. The first change is shifting to the clear input than the preset input. In the previous case, I used the preset input here for the flip-flop number 0, whereas in this case I am using the clear input, and in this way we have all the clear inputs connected to the overriding input. And it is a very important point for the Johnson's counter, because initially when the overriding input is low, you will find that the output Q0, Q1, Q2 and Q3 is low. So initially whatever be the value of the clock, all these outputs are low, whereas in that case we were having Q0 as 1 because this overriding input is connected to the preset and there is no initialization required. Our Johnson's counter will start counting even if we do not initialize it by any 1, but in that case we have to initialize it by having 1 as the output Q0. So this is the another advantage of the Johnson's counter, and because of these two advantages it is highly used. Now let's see what is the another change that we have made. You can see Q3 is not connected to D0, whereas Q3 complement is connected to D0. So these two changes will convert your simple ring counter to the Johnson's counter. Let me revise it down. What are these two changes? The first change is you have to use clear input of the first flip-flop instead of preset input, and the second change is you have to use the complemented output and give it to the input of the first flip-flop instead of Q3, and in this way you will have a Johnson's counter. Let's see how it counts. I have already written the output when the preset input is low, and now we will make preset input high for rest of the cases so that the clear will not interrupt the output. For clock, you can see the flip-flops are negative edge triggered, so all the changes will be there for the falling edge. So this downward arrow represents we have a negative edge triggered flip-flop, and let's find out Q0, Q1, Q2 and Q3. When Q3 is 0, Q3 complement is 1, and this Q3 complement is connected to D0, so D0 is 1. I am finding out the input to all these 4 flip-flops, then we will see the output. So D0 is 1, D1 is definitely 0. All these outputs are 0, and Q1 was 0, therefore D2 is also 0, Q2 is 0, therefore D3 is 0. Now we will find out what are the outputs when we have the first falling edge. I will change the color for this purpose, and you already know in D flip-flop when the input is 1, the output is also 1. So for the first flip-flop we have the output as 1, and for the second flip-flop we have 0 because D1 is 0. Similarly for the third flip-flop we have output as 0, and for the fourth flip-flop we have output as 0. So we have 1 0 0 0. Now we will see what we have for the next falling edge. Q3 is 0, so again Q3 complement is 1. So D0 is again 1, so I'm not doing any overwriting here, I will keep it 1. You can see Q0 is 1, so D1 will now become 1. Q1 is 0, so D2 is 0. Q2 is 0, so D3 is 0, and in this way we have the 4 inputs 1 1 0 0. So the output is 1 1 0 0. Simple. So we have 1 1 0 0. Let's see for the third falling edge. Again Q3 is 0, so Q3 complement is 1, so our D0 is 1. I'm not doing any overwriting, I will keep it 1. Q0 is 1, so D1 is 1. Q1 is 1, so D2 is also 1. Q2 is 0, so D3 is 0. Let's see what we have now as the output. D0 is 1, so Q0 is also 1. D1 is 1, so Q1 is 1. D2 is 1, so Q2 is 1. D3 is 0, so Q3 is 0. So we have 1 1 1 0. So we have 1 1 1 0. In the same way, if you keep calculating for the falling edges, you will find the output as 1 1 1 1, then 0 1 1 1, 0 0 1 1, 0 0 0 1, and then again 0 0 0 0. So this is the complete table for the Johnson's counter, and let's see how we have the 8 states. 0 0 0 0 is state number 1. 1 0 0 0 is state number 2. This is state number 3, 4, 5, 6, 7, 8, and finally we have 0 0 0 0, same as the state number 1. So you can see we have 8 states in Johnson's counter. This is one of the advantages, and you can easily prove it by the waveform. I have already made the waveform here. This is our clock that is given simultaneously to all the flip-flops, and this is the clear input. When the clear is low, we all know that the output of the flip-flop is also low. So Q0 is low for the first falling edge, then it goes high, and Q1 is low for the first falling edge, similarly Q2 and Q3. And now you will see you have 1 1 1 1, then 1 1 1 1. The same thing we have evaluated in the table. In the same way you can complete for Q2 and Q3. This is all for the Johnson's ring counter. The only change you have to make is in the output and in the clear and preset input.